when I put up the lecture notes and everything, hopefully it won't be too confusing. So today, as I said, we are finishing up our review of quantum mechanics. We also did a brief review of classical optics last time, and I talked about where the sort of the regime of quantum and classical optics and so on is. And then today, what I want to, again, so this is just sort of another way to think about the structure of our course. We're going to have essentially two halves of the course, well, within the quantum optics part, which itself is half of the entire course. Within this first half, quantum optics, we have sort of two lines of, two separate parts or lines of reasoning, and accordingly there's a whole lot of different physical effects that are associated with these two treatments of quantum optics. So this is just sort of a repetition of the overall course syllabus, but I think it's helpful. So this is what we'll be going through in the semi-classical atom field interactions, which is where I treat the atom as quantized and the field as classical. Okay, so that's semi-classical. And there we'll see all the very important phenomena that you most likely deal with regularly if you're doing any kind of qubit control, atomic physics, lasers. I'll come back to classical nonlinear optics because there's some connections with the semi-classical atom field interactions when we get to that part. But before that, we have a lot of interesting stuff to go through, which is these items, Rabi oscillations and Ramsey fringes and Hahn echo. And then we have adiabatic passage, which is an important topic. It's a nice analytical and theoretical way to think about many different phenomena in this semi-classical atom field interactions. And all right, and then we'll talk a little bit. Some of this stuff, obviously, I'll be doing at a more high level, and I can ask you guys to maybe give presentations or assign it to homework. Then on the other hand is the quantized atom field interactions, where we fully treat both the field and the atom in a quantum manner. And that gives us important effects, such as why there's spontaneous emission at all, what is the lamp shift, things like Casimir effect, laser line width, photon statistics, photo detection, coherence and correlation functions. And again, some of this I'll only be able to briefly touch upon, some of it I'll go into more detail, and then assign some of the rest to presentations or homework. Okay. So today, essentially, we are launching into this first part, which is atom radiation field interactions. There are many possible references, so I won't go into all of them. But the idea is that we want to first think about what happens to an atom that's interacting with a classical radiation field. So before we do that, then let's finish up our review of basic atomic physics, which will be useful when we think about some of the properties of real atoms, and that we're going to probably think about when we do things like understanding things like selection rules and so on for atoms and their interactions with the radiation field. Okay, so first I'll just run through, first I'll remind you, let's see if I can move this. So of course, the simplest atom that we all learn in quantum mechanics is the hydrogen atom, right? And the Hamiltonian for the hydrogen atom is just P squared over 2m minus E squared divided by 4 pi epsilon naught r, right? That's just the energy of the system. It's one electron bound by the Coulomb force to a proton, okay? And the stationary solutions, the eigenstates En of this Hamiltonian are given by some minus the Rydberg constant divided by n squared. Okay, and those are the bound states, right? Bound states. And then of course we also have the continuum states. For E which are greater than 0, those are the unbound or continuum states of the electron. Okay, so both are solutions of this equation. The quantity Ry, which is Rydberg constant, and its numerical value, of course, is 13.6 electron volts and so on. But it's also a good exercise to know, without solving the Schrodinger equation, to think about how to solve and estimate these energies. Okay, so how can we estimate what the energy of a electron bound in the ground state of a hydrogen atom should be? Okay, so how can we do that? Well, we put in one other fact that we know, which was already mentioned in the last class, which is we know that the electron will satisfy the uncertainty principle, and we're going to say that in the ground state, 0 ground state, the electron will be exactly satisfying the Heisenberg uncertainty principle. So we'll say that in the ground state of this hydrogen atom, the electron is essentially satisfying perfectly the Heisenberg uncertainty principle. And since it's in a bound state, the expectation value of the momentum must be 0, but so all we are left with is approximately that it must have a variance which is given by this delta P naught. Okay, so P squared then of the operator will approximately be the variance of this electron, which from this expression is simply h bar by delta R naught squared. Okay, and so our Hamiltonian H is approximately then h bar squared by 2n delta R squared minus E squared by 4 pi epsilon naught R. Right? Delta. And so to minimize this quantity, just take its derivative with respect to delta R and set it equal to 0. We will find that delta R will be approximately h bar squared by me squared. I think I'm missing some 4 pi epsilon naught. I'll ask you to just fill that in. Okay, well, you can do it. Okay, and wait, where should the 4 pi epsilon naught be? Is that the right energy units?
Is that delta H, delta energy, or just H? It's
the energy. It's the basically the magnitude of the energy, right? Because P is effectively 0 in a bound state. So the sort of the variation in H. Okay, yeah, you could call it delta H. Yes, it's the variation in H with position or whatever. Okay, I made a mistake. I left out the 4 pi epsilon naught. I'm sure by dimensional analysis we can figure out where the 4 pi epsilon naught is. Somewhere. Figure it out. Okay. All right. And then the energy, it turns out, if you then substitute this delta R back in here, you will in fact get the expression for the Rydberg constant that you can look up in any quantum mechanics textbook. Yeah. So, all right. I'll let you fill in the last little blanks. The basic principle is clear. Okay, and now the in addition to just these energy levels, which are given by the, for example, this minimization procedure, which has been made into like a variational principle that you might have read about when you did various things in quantum mechanics. We can also calculate some of the energies of these higher order states and so on. But what we also remember from quantum mechanics is that in addition, that if there are operators A which commute with H, right? if commutator of some operator A with H is 0, then we have a common set of eigenvectors between A and H. Okay? So basically what I'm saying is that in addition to the energy of the state, we also have to label the state by some label, AL in this case, which will be an eigenstate of the A operator, and will also simultaneously be an eigenstate of H. Okay? Pretty straightforward, you all know this from quantum mechanics. And the energy is the same, En, for all of these states, En, Al, and does not depend on the Al. Right? So these levels, or these states, En, Al, all have the same energy En, which means that they are degenerate. Furthermore, if you think about the transformation S hat, which is generated by these operators A, by some, I'll call it phi here, or some essentially some parameter, then applying S, this operator, to these eigenstates, En, Al, these go to S times En, Al. Suppose we operate like this, then we can show that the energy levels are also invariant under this transformation, right? Just substitute back and calculate what happens to the energy levels under this transformation. Because of the commutation between A and H, we know that all of these energy levels are going to be invariant under the transformation. So we see that there is a relationship between the degeneracies and symmetry, right? Because this essentially is a set of unitary transformations, okay, which leaves the system invariant. Okay? So a symmetry operation. And this is of course where sort of the connection between quantum mechanics and group theory begins. We are not going to go into that, but this essentially, talks about how we can start to understand the connection between quantum mechanics and group theory. And we, of course, this is taken into different fields. For example, you could go into a solid state physics class. Then the groups that in solid state physics are important are so-called finite groups. Groups that will carry out rotations of the crystal and so on. Once you have removed all the other symmetries such as translational symmetry and so on, which lead to block wave functions in a solid state class, then you have left behind some other symmetries like rotations and so on, finite rotations, mirror operations in a crystal, etc. All that are symmetry operations of the system, which will give rise to these kind of degeneracies, and all these wave functions will have to be will be degenerate with a certain energy, and you can classify all of the sort of the wave functions of the system based on these symmetry operations. Or if you go into like quantum field theory, then you can think about what are all the groups that elementary particles must have, what kind of symmetries must be satisfied by elementary particles, and so on. For example, angular momentum symmetry, rotational symmetry, that gives rise to a certain group of symmetries. Okay, for the hydrogen atom in particular, the one that we have just been discussing, we know that there are some favorite symmetries, which is the symmetries due to rotation. So this erase this part. That over there. Since we see that the Hamiltonian of the system only depends on the r coordinate, we know that because rotational symmetry must be satisfied, therefore we know that L squared and Lz are also going to be commuting with this Hamiltonian. Okay, and then also the electron spin angular momentum S squared and Sz are also going to be symmetries or conserved or are going to be commuting with the Hamiltonian, and similarly the nuclear quantum number I squared and Iz. All of these are therefore going to be generated from these symmetries, and the energy then En only depends on n, and all the angular momentum states which come from L equal to 0 up to n minus 1, they all have the same principal quantum number. Right? They all have the same principal quantum number n, and therefore will have the same energy. Sorry. And similarly, all the states with Lz equal to minus L up to L, which are the possible allowed values of the Lz quantum number, they also must have the same energy. And so on. So, but of course, this is the ideal hydrogen atom, and we only considered the Coulomb potential. And in the real hydrogen atom, there are corrections to this Hamiltonian, and any real atom has corrections to this simple Hamiltonian. So that will lift some of these degeneracies. So one first sort of lifting of the degeneracy comes from the fact that for example, if you took the same type of hydrogen atom but added more electrons into it, okay, hydrogen-like atoms, which have more electrons in them, okay, then what happens is that as we fill up the electrons into the different energy levels, 1s, 2p, 2s, and so on, these inner shell electrons start to screen out the nuclear charge, right, and create a different potential for the electrons outside in the higher end quantum numbers. And in fact, for a fixed principal quantum number n, let's say, which we think about, like say n equal to 5, right? And for this n equal to 5, we find that those atoms that are further away, which will be in large L states, they have large angular momentum, right? So they're not as closely bound inside towards the nucleus because their angular momentum is large. Then they are less deeply bound because the inner shell electrons are screening out the charge from the nucleus. Okay, and in fact, this can then be formalized. For example, suppose we take sodium. Okay, which is the element with the symbol Na, which has the shell structure 1s2, 2s2, 2p6, and then 3s1. So it has one electron in the 3s level, and the Hamiltonian then, which we can write for this system, is very similar, p squared over 2m for this one electron, minus e squared by 4 pi epsilon naught r, plus a correction term, v prime of r. Okay? And there are different forms that we can use for this v prime. Yes, you have a question? I thought you had your hand up, sorry. Okay. Alright. So there are different approximations that people can make for this v prime of r. Okay. One approximation is simply to say that this v prime of r goes to 0 as r goes to infinity, and then v prime of r is not equal to 0 as r goes to 0. Okay. So it's something that might look like some flat part and then might decay away like this, for example. Okay? These are like pseudo potentials that one can apply to the atom to calculate the effective energy, and in this case, then it turns out that now, of course, E, right, the eigenvalues E is now a function of both n and n. Yeah, so this is one possible approximation. Okay, this is not the only one. There are other ones which are called like quantum defect theory. In quantum defect theory, which is a very common and very sort of robust way of calculating many of these potentials. They also separate out into a quantum defect, where it, what they do is for some r lesser than or equal to r naught, okay, which is a core radius, it's a parameter that you have to find or use or minimize using variational methods and so on. The v prime of r is on the order of something like z minus 1 e squared over 4 pi epsilon naught r. And then for r greater than r naught, v prime of r goes back to looking like something like e squared by 4 pi epsilon naught r. Okay? And so there are various ways in which this quantum defect theory seems to work quite well. So let me just sort of bring back the screen. So there are various approximations. Quantum defect happens to be a prominent one in the literature. Let's see. Right. So in the periodic table, these all of these that are below hydrogen, right, like lithium, sodium, potassium, rubidium, cesium, and francium, these are the alkali atoms. Okay? And as I just said, for example, for sodium, there's one electron outside the core. Okay? And each of these other ones, for example, rubidium, they're similarly, this is the core, one has, all up to 4p6. And then starting from the 5s level, okay, you get one electron. Okay? So that's in the 5s level that you get that one electron. So these alkali atoms are very hydrogen-like, and so they are what people have started with, and they are in fact examples of many of the atoms that are being currently used in a lot of what we call this ultra-cold atom physics. For example, rubidium was the atom that was trapped first in a BEC, okay? And I think the other one was lithium that was trapped in the other BEC that was created at the same time, or maybe it was potassium, I can't remember. But anyway, so the wave function, okay, this just summarizes same things that I've said. There is a core wave function corresponding to the filled shell, and then we can treat the valence electron, the one remaining electron, just like a hydrogen atom, and as you can see, the wave function of this system looks just like the hydrogen atom. There's a part that's dependent on R, and then there's a part that's just the standard spherical harmonics for the hydrogen atom. Okay? So yeah, and the electron core is frozen, which provides a sort of effective pseudo-potential for the valence electron, and the description of the valence electron becomes a single electron problem, which will obey this particular equation, which is just the Schrodinger equation in 3D. Okay. So the choices for this V of E, V of R. Okay, in this slide, Dr. Daly, from who I got this slide, he has not done this separation. So I did this separation where it looks like a hydrogen atom plus V prime of R. Okay, and then the V prime of R might have a Z of Z minus 1 because we've already taken care of that part. But anyway, in this, what he has done is just combine that. So for R lesser than R naught, it goes into the standard, multi electron wave function, or a single electron interacting with a core which has a charge of Z times E. Okay, and then the outside, far outside the core, then it goes into this E squared divided by 4 pi epsilon naught, as if it was just interacting with one proton inside the core. Okay, and so for a review, you can see this particular paper from 1980s. And the nice thing about this spectrum, as you can see here, the spectrum looks very hydrogen-like. Okay, so the energy spectrum looks like the Rydberg energy divided by some new NL, where mu NL depends just on n, the principal quantum number, minus a defect. This is called the defect, okay? Because it's the difference between the original n that would be predicted by a simple hydrogen atom model and the actual energy of the system is just differing by this mu L. The mu L, which is the effect, the quantum defect, and that is approximately, as we say, is not a function of the energy. It's not a function of n. It's purely dependent on n. Okay, approximately in this model. Okay, but that's a nice thing about this model, and that's why it became very helpful for people, because it allowed you to calculate all the energies of these systems without having to do too much numerical calculations. Okay? Because of course there are models for multi-electron atoms which take into account the full energy of the system, including all the different interactions between the electrons, interaction between the electrons and the other electrons, interaction with of the dipoles, and so on and so forth. Okay, but this one is a nice simple model that allows us to find these energies. So the next thing, which I was going to talk about, but maybe it's easier just to go through it in the slides here, is to consider the fine structure of an atom. And you'll see the fine structure also show up in many other systems. Okay, so it's not just unique to atoms. Almost any system has some symmetry, and usually that symmetry gives rise to some set of energy levels, right? Like I was just discussing, in a solid state, say quantum dot, you might have a set of symmetries for the quantum dot, which is some confined potential, and that will give rise to some symmetries that are similar to a hydrogen atom. In fact, some of the energy levels in a quantum dot in a solid state system are labeled by like S, P, and so on, very similar to a S and P of a hydrogen atom. And in that case, then also you have to consider fine structure, which is the breaking of these symmetries, which is there are always some other interaction that breaks these symmetries. And the question only is one of magnitudes, right? So you first start with the strongest interaction, you diagonalize your system into that interaction, and that gives rise to a set of energy levels which will satisfy some symmetries, okay, which are commuting with that original Hamiltonian that you chose because it was the dominant interaction in the system. But then you start to see all these little perturbations, and these little perturbations break the interactions or break the symmetry of the system, and that gives rise to fine structure, which leads to splittings of these original eigenstates of the Hamiltonian. Okay, so for example, in a hydrogen atom, it's well known, right, that there are relativistic corrections to the energy. Okay, so if you go back and look at your undergraduate quantum mechanics or graduate quantum mechanics textbook, and if you look at the later chapters, maybe if you didn't get there, I don't know, but there are relativistic corrections, for example, first to the kinetic energy. Okay, that gives rise to something called Thomas precession and so on. Okay, then there is a relativistic correction to the spin and orbital coupling, which is spin-orbit interaction. Okay, and finally there is something called the Darwin term, which is a correction to the potential energy of the electron, which is experienced because it looks to the electron as though the nucleus is moving really fast, and that gives rise to a change in the potential energy. Okay, so those three are all important to different magnitudes or different effects. And I haven't even considered things like, what about the interactions with the core, right? Remember that we were just talking about. Maybe there is some parts of that interaction with the core that, see, this quantum defect, the nice thing about it is it's still spherically symmetric, which is what allowed us to use the same types of wave functions as for the hydrogen atom. But there are, obviously, even to this quantum defect or any other potential that you might come up with that's purely R dependent, there will be corrections that are theta and phi dependent, right, which break the symmetry of the system, spherical symmetry of the system. For example, interactions with other electrons. Interactions with some of the core shell electrons that is not satisfied purely by the central potential will look like terms that will no longer commute with L squared and LZ and so on, and that will break some of those degeneracies. Okay? So there are all these different potentials, and we have to consider what happens to the atomic physics in the presence of these other potentials. So one of the most important ones probably is the spin orbit interaction, right? L dot S, and this of course comes from like the Darwin term, which I should mention, is usually only non-zero for S states, L equal to 0 states. Okay, so the Darwin term can usually be neglected unless you're dealing with S equal to 0 states. And similarly, we'll see when we do hyperfine interaction that the hyperfine interaction tends to be very strong for S equal to 0 states because it has a very strong component at the nucleus. Okay, so but for P states and so on, the spin orbit interaction tends to be the dominant term. Okay, and so this S dot L, this term up there, I wrote it up there, S dot L, right? That's the spin orbit interaction with some coefficient A typically that is given to it. Then we know that the spin orbit interaction S dot L will commute with S squared and L squared, but not with LZ and SZ. So LZ and SZ are no longer good quantum numbers, but instead we can make a new degree of freedom or a new angular momentum J equal to L plus S, with which L dot S will be commuting, and therefore the new degrees of freedom are J squared and JZ, which are the good quantum numbers. Okay, so we can label the states by J squared JZ and S squared L squared. Okay, so if you want to write the system in terms of the old quantum numbers, then we end up with these coefficients, right, which are just coefficients of the expansion in the different bases, right? These are called the Clebsch-Gordan coefficients, okay? And they are tabulated, so I won't go through how one calculates them and so on, but these are just well known in the system, and we know that the J, the total angular momentum quantum number, must take these values, going from plus L, from L plus S to L minus S, okay? And the notation that's adopted for multi-electron systems, in this case rubidium or whatever, is there is an N which denotes the principal quantum number, and then to label the states you have 2s plus 1 on the superscript L comma J and subscript J. Okay? And so for example, the ground state in the system is 5s 2s 1 half. Okay? So that is the state, and because S equal to 1 half, right? So 2s plus 1, that is giving you the 2. And the first excited state then is 5p 2, but then for p it can be either 3 halves or 1 half. Okay? So those are the two states which are just shown here, and the typical energy splitting between these two is on the order of a visible or infrared sort of wavelength, 780 nanometers, and then there is a fine structure, okay, because of the effect of the spin orbit interaction. Okay, so that splits those J values, okay, J equal to 3 halves and J equal to 1 half are split by the spin orbit interaction to be on the order of 7,000 gigahertz. Sorry that there's a change in the units. This will be very common. When you see fine structure, a lot of times, because it's such small energy splittings compared to visible wavelengths, right? 780 nanometers in the terahertz, right, regime. So, or 100 terahertz, something like that. And so this is obviously a much smaller energy compared to that. Okay.
Does SPIT have a demo experiment for this, for advanced?
For rubidium?
Yeah, is this a simple demo?
It is pretty simple.
You can
we
buy
have sodium.
You can buy it for from TeachSpin.
We have sodium.
And you have the sodium.
Yeah, we don't have rubidium. Right. Yeah, but you're right. We could buy that and see the different. Have a laser scan across.
Mm-hmm.
Right.
Yeah.
Yeah.
With
we do it with a spectrometer.
Diode.
We could do it with a diode laser.
laser.
Absorption spectrum.
Grating stabilized.
Right. And then if you look further, so this is shown over here, then again the same thing, but now we are also labeling the mj equal to minus half and plus half, which is allowed, right? The j and jz are the valid quantum numbers, And then you see that there is this multi-level degeneracy in this system. Okay. And then further, these levels are further split by things like the hyperfine interaction. Okay. So the hyperfine interaction will further split some of these levels. The hyperfine interaction, if you haven't seen it, let me write that. Have you seen the hyperfine interaction in quantum mechanics? Yes. You've seen the spin orbit, right? Okay. What about hyperfine? Have you calculated hyperfine interaction as well? Maybe not. This is a very useful, the hyperfine interaction comes up again and again in various systems, so I think it's useful to describe it once. Any questions so far? Yeah.
Maybe it's a correction because so the quantum defect model, the V prime,
Yes.
at R greater than R naught,
Yeah.
right? Wouldn't that cancel with the potential? Maybe should it be 2 times or something?
Oh, right, yeah. You're right. Thank you.
Yeah.
Yes. Maybe it should be
2 times?
minus.
Or is it a minus?
Right. Okay, let me see how to write this. So for R greater than R naught, we have E squared by 4 pi epsilon naught R. So
Yes,
this
you
should
should
go
end
to,
up-
actually this should go to 0, right? That's what it should be. In this same, if I were to use this same
Right, it would go-
model, it would go to 0. Sorry. Thank you. I was thinking of the total potential again,
Mhm.
and I got confused. You're right. Thank you.
Okay.
Right. So for R greater than the core, this is like a constant potential. This is one of the models that people have used. And then this is a better potential which people have used, which is the quantum defect model. Where in both cases, I guess for R greater than some radius, the V prime goes to 0 because you still have the piece that you normally have. Thank you. Okay, so hyperfine interaction. It looks just like a dipole-dipole interaction between the nucleus and the electron. Okay? Plus one additional term, which is called the Fermi Contactor. Okay. So the it can be written using sort of this. Let's see. I'm going to write it in a second. It's just S dot and have So this is an Mn, which is the magnetic moment of the nucleus, will be governed by this. Okay. So you can see there are 2 parts of this interaction. So this is just like a dipole term, right? This is the dipole moment of a maybe this should be G. Okay. So This is the magnetic moment of the electron, and then this is the dipole magnetic field from the nucleus, plus a term which is the contact term or the Fermi contactor. So this is dipole, and this is contact. And you can immediately see, because of the delta function, right, in this thing, that it will only work for those wave functions of the system, because of course multiplying when you evaluate such a correction to the Hamiltonian, you're going to have those wave functions that are going to need to be evaluated with this function, say delta of r or 1 over r cubed. And if delta of r is only non-zero at the nucleus, that means that the wave functions that have a zero at the nucleus are not going to show up. And most of the higher L wave functions, for example P or D wave functions, etc., are not going to have any component at the nucleus itself, and they're going to vanish in this Fermi contact term. And these other guys are all going to be divided by r cubed, so they're going to be weaker. Okay? But as I said, for these higher angular momentum states, L, etc., P states, and so on, this term is going to be the dominant contribution, which looks just like a dipole-dipole interaction. Okay? So in general, the hyperfine energy or the perturbation of the hyperfine interaction is going to have some thing, which is this now the hyperfine potential or the hyperfine term, hyperfine interaction, times I dotted with J. Okay? When you evaluate this for the electrons in a typical system, this is what it's going to look like. This is an approximation. We drop some of the other terms in the system as being weaker and so on, but you can take them all into account if you really want to. Okay? And then in this approximation, then the angular momentum that's conserved is the one that adds up all three of these angular moments. The nuclear spin, the electron angular momentum, and the electron spin angular momentum. Okay, from here I'll skip some of the things, like for example you can calculate what happens to such states when you put on some external perturbation like a magnetic field or electric field. This is all just standard perturbation theory, and you can calculate things like something called the Landé G factor in the presence of a magnetic field, which will depend on all of these quantities like J and L and S, basically. Okay, so that tells you like the splittings of the nuclear magnetic field or the splittings of the electrons when in the presence of a nuclear spin will be dependent on F and J and I and so on. Yes.
So
did I make a mistake?
No, I just have a quick question.
Yeah.
So if I want to deal with this Hamiltonian,
Yes.
like the total Hamiltonian for Heisenberg,
Hyperfine.
Hydrogen light.
Yes.
So is this a higher order perturbation compared to the spin orbit?
Yes.
So that means they do have like a hierarchy.
So if you look at, in that earlier slide that I had shown of rubidium,
Yes.
MJ levels are all degenerate, and then when you add this in,
Yeah.
it lifts the degeneracy.
Okay.
So it's but by smaller amounts, by like tens of gigahertz, for example,
Okay.
when in the presence of these interactions.
Okay.
So it's much smaller than the fine structure splitting, which was on the order of 1,000 gigahertz.
Yeah. Okay. So what is the small number to control this perturbation theory?
What small number?
I mean,
It's the dipole moment of the nucleus, right? Because it's 1,000 times smaller,
Okay.
or 2,000 times smaller than. dipole moment of the electron. So,
Oh, okay.
yeah.
This contact term, the second term, where is it? Where's that from again?
Oh, right, yes. I have looked into this before, so let me think about this for a second, but I can't remember the answer off the top of my head. Sorry, I'm drawing a blank. I know I've looked it up and I've seen what it is, but I must not have understood it deeply because I'm not able to reproduce the argument for you right now. Let me think. What was that?
You can look it up.
Huh?
You could look it up.
Oh, yeah, no, I know, but I think we have to think about it because
Yeah, it only acts at
Yeah,
distance
so-
r specific.
right. So the point is that you have you have a nucleus and you have the electron. So obviously the first inclination is to say that the only energy between them is this dipole-dipole interaction, and that's easily understood in a classical way, right? Because it's just the. I think this term, what it comes from, if I remember correctly, and it's vaguely coming back to me, is the idea that I think that the nucleus in the frame of the electron looks like it has some angular momentum. Has a orbital angular momentum, okay, which gives rise to a current and therefore an interaction between the magnetic fields from that current of the nucleus. Does that make sense? And I believe that's the reason, but I think we should be careful and look it up. So it's a little bit more tricky, right? To calculate also. You have to be careful about relativistic corrections and things like that with this stuff.
And this is, it seems like a dominant term because it doesn't have the R cube.
Yes, so it's dominant relative to the dipole-dipole interaction, but it only exists right at the position of the nucleus. So if the wave function of the electron has no probability to be at the nucleus, which will be true for all the higher L states, then this term will vanish. Okay? That's also because of this sort of this current loop argument, basically.
Okay, so it's simply, it seems like it's contact when if the electron in the nucleus.
Well, if the electron has a probability to be at the nucleus,
Yeah, then that would be.
then that is why this term is there.
It's like a spin.
It's like I think taking like the field from the electron
Yeah.
and seeing if it has some.
Kind of like a
component.
spin magnetization.
Yeah, like the Heisenberg, say, for example, term, right? Because that's exactly what this will be, right? Mn dotted with S.
Okay.
This will be I dot S also.
So R is the radius of the nucleus.
Right. Right.
Okay.
No, R is the distance. Essentially, it's just the distance coordinate between the nucleus and the electron. Just a standard R cube. Or R squared.
R, yeah, it's R.
Yeah.
Okay, so it's not the same R.
So if you had two dipoles, then this is exactly the interaction you would write down, right?
So I'm saying it's.
If you have two dipoles, P1 and P2, then you can exactly write down this energy, which is just a P1 dot P2 minus, so this is the 3 P1 dot R times P2 dot R divided by R cube minus P1 dot P2 divided by R cube. So that will be the interaction energy between two atoms, right?
Yeah.
P1.
I guess what I'm saying
R.
is there are two R's there,
P2
and they're not the same R.
No, they are the same R.
R is a variable on the left term, and the other one is
It's the same R.
when delta R.
It's the same R.
Yeah, R is 0. Okay, yeah.
It's the distance between.
You're right. Yes.
This is the
Sorry,
R that I'm
yeah,
writing.
you're right.
Okay.
My bad. You're right.
That's okay. Good to look at. If you've never seen it, then I think it's good to look at it once to say that, this is
Contact.
this is different here. So this is the standard magnetic or any dipole-dipole potential energy, right? has this form. 3 times P1 dot R times P2 dot R minus P1 dot P2 divided by R cube. Okay, and that's exactly this first term here. Okay, so this is very classically understandable in the sense of a dipole-dipole interaction. This term, as I said, is a little bit harder to understand. But I think it's because of that effect, that in the frame of the electron, the nucleus looks like it's a current. And that current then has a magnetic field at the position of the electron. Okay. Is that what you're seeing? I don't know, I see you're looking on the phone. Is that what it says? Maybe I'm wrong. So you should
I
correct me.
understand the Wikipedia actually.
Oh, you can understand the Wikipedia. Yeah, it's hard to understand the Wikipedia. All right, we'll think about it. I'll look it up again. Thank you for bringing it up. Okay, so we have covered sort of basic atomic physics. This will be helpful because we can make analogies to this for almost any qubit atomic-like system. So, for example, just last couple slides. So we saw the rubidium atom, which is this sort of nice looking structure. If you took a 2-electron system now, the number of levels skyrockets, right? Because there are so many more possibilities. But the amazing thing about atomic physics, at least, right, this is why atoms were the first sort of qubits that people were looking at, is everything is understood about them, experimentally, and we know all of the energy levels, all of the transition wavelengths, the hyperfine structure, the fine structure, the hyperfine structure. So here's strontium in all its glory, right? I mean, you can pick any number of levels here that you want to work with, find a laser that can hit them, and you're in business for quantum information processing, like as we'll talk about also later on in the class. But everything, you can see the kind of precision too with which some of these energies are known, right? Down to like sort of part in 1,000 type of precision, right? So,
are those in gigahertz, the numbers?
well, I think those might be, let me see. Some of these are nanometers. Yeah, I think some of these are gigahertz, basically, right? Exactly. So that's like 34,000 gigahertz up there, for example. Or this is 14,898.563 gigahertz. Okay, so
Up to
it's known to like terahertz to like
megahertz?
megahertz out of tens of terahertz. So it's extreme precision, right? Part per million. Sorry, not even part per thousand. Okay, and so that's exactly why, for example, one of the first qubit systems that was used was the calcium ion. People understood all the energy levels and the splittings in that, and they could trap it using so-called Paul traps, which were electrostatic and combined electrostatic and RF traps that allow you to trap an ion in a single place and then just study its properties and use it as a qubit. But then, as I said, we have other qubits like quantum dots, for example, or the solid-state version of these of atoms. And their electron and a hole are trapped in a band gap or in between two dissimilar materials. Like one of the famous ones is cadmium selenide and say zinc selenide. And what you can do is that the outer zinc selenide has a higher band gap than the inner core of cadmium selenide, and so the electrons get confined within the conduction band, and the holes get confined in the valence band, and then you can have this confinement energy, which gives rise to these energy levels. It's like a box basically, and you can calculate the levels in a box, a square well, for example. You can be more sophisticated, of course, if you're in solid state and do all the calculation. But effectively, you get some energy levels, and then you can get fine structure at the energy levels due to the electron and hole angular momentum, just like we did for the atomic physics. And you can get hyperfine interactions between the electron and hole and the nuclear spins of the host material. So for example, cadmium selenide, cadmium has some nuclear spin, and so that will have affect a hyperfine interaction on the energies of these electron hole pairs, for example. Similarly, we can have for NV centers in diamond, now the energy levels are labeled by the symmetries that are relevant to the NV center, which are not the full spherical symmetry, but they are group symmetries, finite group symmetries inside the diamond lattice, which are labeled by these, but the same type of labeling, like you have, this 3, which is a 2 electron system, so it has S equal to 1, and therefore the upper index is 3, and then it has a orbital momentum, which is labeled by something called A, which is a different symmetry of the system, and then there's another symmetry, which is E, which looks like A will be roughly looking like a S-like state, E will look roughly like a P-like state. So it's very similar in the sort of the shape of the wave functions. If you look at the actual wave functions, then one can calculate all the symmetries, and then you have fine structure, okay? Due to similar interactions, there's fine structure, and then there are many other levels as well. Okay? So anyway, so that's just an idea. You go to something like a transmon qubit. You have various states, and maybe we'll have someone from Hatridge group tell us more about transmon qubits. But basically, there are other similar effects of like first due to the potential is different. It's more like a harmonic oscillator, or slightly modified harmonic oscillator. And that gives rise to different levels over here, and then you can also have other kinds of fine structure and so on. Okay, so let me conclude sort of this review. The thing we now want to talk about is the interaction with optical or electromagnetic fields in general, right? Remember that we are now in the semi-classical atom field interaction part of the course. So we want to discuss how a classical optical or electromagnetic field will interact with these atoms that we were just discussing. Okay. So to do that, we will first introduce what that interaction is going to look like, and then we're going to discuss the selection rules. So we know that, for example, for some atom, the typical Hamiltonian for the atom is going to be p squared over 2m plus, say, some V of r. For a real atom, whatever it is, so some other atom, quantum dot, whatever it is, it's some potential that we have to look at. And now we want to bring in the electric and magnetic fields E and B. Okay? So how do we include E and B into this Hamiltonian for an atom? Okay. What happens to the operators P and R in the presence of a electromagnetic field E and B? Or can we write them in terms of E and B? What is more classically? What is more done? What are the things that we normally do when we have an electron that's interacting with a magnetic field or an electric field. What types of things do we consider? Do we directly take E and B, or do we take something else? Maybe it's been a little while, so maybe I don't know if you remember.
It's a point.
So what we do instead of looking at E and B directly is we look at the scalar and vector potentials, A and phi. Okay. And when we have A and phi, then we have a very different Hamiltonian now. In fact, we can show that this Hamiltonian becomes P minus QA whole square divided by 2m, where of course A is now a function of R and T, so these are all functions of R and T. Plus Q phi, which is expected, R and T, plus V of R. Okay? So our Hamiltonian is now in terms of the vector and scalar potentials, where, as you know, B is equal to del cross A, and E is equal to minus del phi, and there's a dou A over dou T term, but I don't remember the sign. Maybe I'll see it later. Okay, we'll find it later maybe. Okay. Yes, it's actually minus. There it is. I don't know. Good. And if you are wondering how you get this from knowledge of the vectors of those equations, I don't know if you've seen that. Hopefully you have. In classical mechanics, right? It actually all comes from classical mechanics. So that's why knowing classical mechanics is still helpful, right? Even though everything is quantum, that is, we start with, I'm just giving brief aside or sketch of the proof. Okay? This is not relevant to the rest of the course, but just a reminder that you have the Lagrangian, right? L, which is equal to T minus U, and U is a generalized potential now. Which governs any generalized force. Qj is dou U over dou Qj plus d over dt dou U over dou Qj dot. Okay? And that combined with Euler-Lagrange equations gives us the equations of motion classically for a particle. Okay. So if I take in classical mechanics, a particle will have L equal to half mv squared, right, minus U, where U now I will take as Q times phi, which is understandable, that's just the potential energy, Q times the potential, minus Q A dot. Okay? So that is the Lagrangian for a particle that's moving with some velocity v in a electromagnetic field which has a potential phi and a vector potential A, which governs the B and E terms there. And so you can see if I put this back into the Hamiltonian, I'll get this term which goes as QA, which modifies the momentum of the equation. And so yeah, so I mean, to show this, well, basically what you do is you consider, say, the x component, right? To show that this is indeed the Lagrangian, you take the x component, substitute dou L over dou x dot. I won't carry through the steps, but then basically, if you calculate dou L over dou x dot and substitute it back into the Euler Lagrange equation, you'll end up with, after a little bit of algebra and then using the definitions of B and E over there, you'll find mx double dot is equal to q times Ex plus B cross B x component. And that, of course, is the Lorentz force. So this is how we know that this Lagrangian must be giving us the right equation of motion for a particle in an electromagnetic field. Okay. All right. That was just an aside. It's not important. If you don't care and you want to accept that this is correct, then this is indeed the expression for a Hamiltonian of a system in an electromagnetic field. Okay. Now, what is our? So I'm going to erase this since this is not too important. I should have probably written the backside. So remember, our goal is to find out what is the equation of, or to find out what is the interaction between the atom and the electromagnetic field. And you could say, well, yeah, we are done, right? I mean, we have P minus QA over 2M plus Q phi. But of course, in the lab or something, what we generate are the electric and the magnetic fields. Okay. So we would rather write this Hamiltonian not in terms of the vector potential and the scalar potential, but we'd rather write it in terms of E and B, because that's what we are going to set up in the lab, okay, in an experiment. So to obtain the same Hamiltonian now in terms of E and B, we will make a gauge transformation and some approximations. To obtain a new Hamiltonian, H prime, which is P squared over 2M minus mu dot E, where E is now evaluated at 0, which is the position of the nucleus or whatever, plus V of R. Okay? Where mu equal to Q times R is the dipole moment operator. And so what are the two assumptions or the two approximations that we make? So well, one is more an assumption than an approximation, which is that we're going to work in the Coulomb range. Which is that del dot A equals 0 and the scalar potential phi is 0. Okay. And the other, because we know things should be independent of gauge, and so we just choose this particular gauge. And the other approximation that we make is sort of a long wavelength approximation, or effectively we say that A of R comma T is approximately A at 0 comma T, where R is of course the distance from, so R equal to 0 is the position of the nucleus. I we are saying that this is much smaller than the wavelength of the electromagnetic field, so that we can just evaluate the electric field at the position of the nucleus and don't have to worry about how much it varies from the nucleus to the point of the electron. Okay? Because the position of the electron is given by R, and I'm saying that the value of the electromagnetic field E is the same at the atom's core and at the electron's position. Okay? So any variation is much slower than a wavelength line. Of course, you can do better than this. You can look at terms which are taking into account the full multipole expansion. You can multipole expand the electric or magnetic fields, right? And then you get the higher order terms, which are varying sort of on this order. And then those will come in as the magnetic dipole term and the electric quadrupole term, and those will all be on the order of 1 over the fine structure constant smaller, okay? Or the smaller by a fine structure constant, okay? I'm not proving those statements, but you can look those up in various quantum mechanics books. So how do we obtain this new Hamiltonian? This is our goal. So what I'm going to show you now is that we obtain this new Hamiltonian by making a gauge transformation. The gauge transformation is psi going to r comma psi. Remember, I will write down our original Hamiltonian here just to remind you. The original Hamiltonian was P minus QA whole squared divided by 2m plus Q phi plus V. Okay? And that, of course, we normally put into the Schrodinger equation, IH bar dou psi over dou t equal to H psi, right? So we are saying that normally this would be the Hamiltonian that governs the time evolution of the state ket psi, but now I'm choosing a new state ket, r times psi, okay, where r is given by e exponential I minus I q dot q r dot a divided by h bar. Okay. And notice that even though this looks like it's simple, this a is a function of r comma t, right? So it's a complex. When you think about what this transformation is doing, it's taking the value of the vector potential at a certain point r and carrying out a sort of a local transformation on psi, right? So it's at every point r, this transformation is different, right? Because it takes into account r as well as the position, the dependence of the vector potential a on r comma t. Okay. So it's a pretty interesting transformation, but it's just a gauge transformation, right? Okay. Under the action of this transformation, we had to calculate the new new wave function, right, or the new evolution equation for the Schrodinger equation, right? And to do that, first I'll remind you that if I have IH bar dou psi over dou t equals to H psi, and I now transform psi to r comma psi, I have to worry about exactly how to do that by this process. I'll just quickly write it, right? So if I take some psi going to r psi, then in this new transformation or in this new system, there is a extra term, right, which depends on dou r over dou t times psi. Okay. So d psi over dt I re-express in terms of the Hamiltonian. So that is just d psi over dt is just h divided by ih bar times psi plus dou r over dou t times psi. Okay? And since r is a operator, so psi goes to r psi, that means that I can re-express this in terms of psi prime. Psi prime equals r dagger times, psi equals r dagger times psi prime. Okay? So remember, this is psi prime. Okay? I'm trying to find out the transformation of psi prime under the effect of this operator r, which means that this whole quantity here can be written as ih bar r h, ih bar cancel, r times h times r dagger times psi prime, right? Because psi equals r dagger psi prime plus ih bar dou r over dou t times r dagger psi prime. Okay, so all I'm saying is that under the action of a transformation R, the evolution of this new state get psi prime goes as what you would normally expect, which is just RH R dagger times psi, the psi prime, which is the state get that you want to calculate, plus this term which depends on the time evolution of that rotation transformation, of the unitary transformation R. Okay? And normally, most transformations are not time dependent, so typically this term will be 0, but in our particular case, we've chosen a gauge transformation which is explicitly time dependent, so we have to include it in this calculation of what happens to the state gap. Okay. So now we go back to the Hamiltonian H. How much time do I have? Okay, I'm out of time. So what I'll do is in the next class, I'll come back to show, this is the program, right? We want to put all this in and show that it's equivalent to this Hamiltonian H prime over here. Okay? That's it for today.
So where is the Coulomb gauge come into?
When I substitute this and put it back into that Hamiltonian H, I'll find that I'll have terms that involve things like del dot A, and I'll have to set them to 0.
But we have already used that gauge, right? So
Which
we can
gauge?
now apply the R gauge transformation and then do a Coulomb gauge.
Say that again.
So
We have applied the unitary transformation, correct?
The R is just like a gauge transformation, right?
This R is a gauge transformation, correct?
So when we apply this gauge transformation, could we still choose the Coulomb gauge? I mean, well,
Why
why
not?
not affect the Coulomb gauge?
No, gauge transformation, I'm just working in the state of psi. I've said nothing about what happens to the electromagnetic field under this gauge transformation. I mean, you can call it a gauge or a unitary transformation, okay? It's some unitary transformation on psi.
It's a translation, is it?
It's a transformation.
It's a
Because it makes
translation
psi-
of the wave function.
Well, yeah, I mean,
It looks like a translation.
well, no, because it's got R here. So it's, how does it, yeah, that's true. A translation in e to the minus I p r, p dot r, right. So, yes, it does look like a translation in the momentum space by p, right, where p is this q times a over h bar. So basically that's what we're doing, right?
It's the same
Because if
thing.
you looked at this original Hamiltonian, that's what it is. It's transforming p to p minus qa. So the corresponding operator in the radial space, right, in the coordinate space, that will look like a transformation of the psi by this operator over here. Okay.
A does not, the Coulomb gauge doesn't come into effect yet.
Yet,
It's just-
it has not come into effect yet. But when it will come into effect in a minute, when we put this into the Hamiltonian and transform the Hamiltonian. At that point, at some point, we'll come across terms like del dot A, because P has, gradient operator. And so we have to at some point find those del dot A's and things like that. And that will vanish.